most of the time, it will expel it, and it will drop out liquid water. So I have got to understand that these systems have got the potential, at least, for all three phases to flow. So this idea of reservoir quality becomes a really sticky wicket. I raised the issue about viscosity. See, I just went full circle, because I've just understood now these reservoir systems are probably multi-phase flow systems, and I've got to try to come up with an understanding of how to measure the quality of that system. The next piece of it is the size of the stimulation. If all I did on a well was an acid job, I assume you've had some completions at this point and you're familiar with acidizing a well versus doing a frac job, in spite of how socially incorrect. One of the things, just so you get a clear understanding, I've gotten a couple of awards for the work I've done on hydraulic fracturing. I was responsible for about 20,000 frac jobs in the DJ Basin. So I am one of the lowest forms of life if you talk to people in Boulder, Colorado, because it's illegal now to do frac jobs in Boulder County. Hello. One of the things I would love to have happen, I'm serious, don't get me wrong, I'm serious. One of the best things that could happen to our industry is for the U.S. to outlaw hydraulic fracturing. What? No. Yeah. Think about what the oil and gas price would be in about 2 weeks. People are complaining about $5 gas in California now. Oh, get a life. 30, 40 bucks a gallon would be, bottom line is, if you stop and look at the slack in our supply system, to do away with hydraulic fracturing would be the best thing that could happen to oil and gas price. Because about 2 weeks in, it would be so high that everybody would come back on their knees. Please. No, that's another story. Anyway, a well that has been acidized compared to a well that got, the largest frac job I ever pumped was 25 million pounds of proppant. That's a lot of proppant. That's a volume of proppant about the size of 2 of these rooms. Just to give you a sense of how much stuff it is. It's huge. Now, was it smart? I didn't ask that question. It was stupid. It was absolutely, categorically, but it was cool. It was so fun. The job pumped for 3 solid days, 24 hours a day. Did we do much better? What we found out was my 25 million pound frac job was no better than if I pumped about 500,000 pounds. But, hey, I was really doing something important here. I had 3 different Halliburton crews on location. I was a big dude. Reality is the pits. Anyway, size of stimulation. Obviously, there's a point of diminishing returns. That's one of our tasks, is to find out where that is. But clearly, well performance has got to be a relationship of stimulation. Aggressiveness of production. We're going to get into that thing, and I'm going to beat up on that like no other. Operating pressures. One of the ideas, and the reason this is important, you say, well, I thought you were going to talk to me about well testing. I'm not going to talk to you about well testing. Well testing is a tool to evaluate how to make money more effectively. And when I say effectively, one of the pieces of that discussion has to be the risk. Everything we do in this industry, there are only 2 professions in the world that have the luxury of burying their mistakes. And the good news is, ours were already buried. The other guys that bury their mistakes, are the medical doctors. See, there's the plus. Ours came buried already. They were not. Get it? Anyway, sorry. That was not bad. That was. Notice the bottom line there. Notice the bottom line. Amount and timing of shut-ins. See, we use that phrase, amount and timing of shut-ins. When we talk about shut-ins, we sort of suggest that I'm going to suggest to you that's bad. But in the well testing class, we tell everybody that's good. A very good friend of mine is very famous for their marketing of shut-ins. And yet this person is wanting to consider the possibility of switching hats and coming and talking about floating. Well, this becomes an issue, and we need to look at how it affects the performance of the well. So those are the things we need to consider. Simplistic approach can be misleading. In John's paper, he made the point, let's go read the sentence here, there's a terrible graph. When we attempt to find constants in the Arps hyperbolic decline equation for resource plays, best fits require values of B, the curvature, to be greater than 1. Arps said in his original work that only exponentials would work, or that B could not be greater than 1, and yet they do, they have to be. This was offensive, because changing that value of B, if you make it big enough, that curve goes flat, and you can get any reserve figure you want. So that was one of the big issues. When we do the forecasting, which is obviously the agenda when you're doing an estimated ultimate recovery, we would like to use, oh, in the right place. Sorry, thought I bumped the curve. What we want to do, and this is perhaps the most important thing that John said, to forecast future production, use a combination of material balance to relate cumulative production to average reservoir pressure combined with the deliverability equation. We know it as I'm going to use the pressure transient equation to relate withdrawals with the difference in the current reservoir average pressure and flowing pressures. This idea right here, the difference in the average pressure and the bottom hole pressure, one of the things that's implicit there, and some of the examples we're going to look at, you'll see this come up. It isn't so much necessary that we have the pressures at bottom hole, at the sand face. For example, in the Piceance, northwestern Colorado, in the Piceance, we have completions, top of perfs are at, for discussion purposes, 5,500 feet. Bottom of perfs will be at 9,300. Nearly 4,000 feet of vertical thickness. So this idea of bottom hole pressure, and especially if you've got some water standing in the well, really becomes kind of a sticky wicket. What I need to do is have the pressures measured at the same datum. All right? So when we talk about this, when we start thinking, one of the things, I am guilty. You know that thing about pointing at somebody and their 3 fingers pointing back at you? Well, that's an issue for me right now because I taught these things, and I taught them from the perspective of too simplistic a view of the universe. Because all of a sudden, I've looked at these horizontal, my record in looking at horizontal wells, one of my clients actually presented me a horizontal data set, production data from a horizontal well. The horizontal was 23,000 feet long. 23,000 feet, 5 miles almost. Had 75 stages in it. The epitome of stupidity. I mean, this company did it because they could, not because it was valuable. But they were proud of it. Hey, look what we did. You know, well, I also pumped 25 million pounds of proppant, and that was stupid too. But when you get into this issue, and you start wrestling with these kinds of reservoir systems, and the way we access them, you're suddenly confronted with the fact that we need to make sure the tools and the approach to that are consistent with the problem that they pose to us. Another data point. In Green River, in eastern Green River, Jonah, and you've heard of Jonah, Nerd River, and all that stuff. In the eastern Green River, we're looking at completion thicknesses that approach 2,000 feet. Okay? So this idea of this datum pressure is really an important one. When we wrestle with those ideas, and you say, well, I'm going to do a build-up analysis. Well, consider the fact, if you've got 4,000 feet of reservoir section contributing to your wellbore, okay? Under 4,000 feet of vertical section contributing to the well, is it probable, is it likely that all of that section is contributing all the time? What do you think? 4,000 vertical feet. I mean, back in the day, we completed wells that were 20 feet thick. And we worried about thick reservoir sections, 20 feet thick. Now we complete 4,000 feet and do it every day. Don't you think maybe that changes the way the rules of the game work out? Absolutely it does. The problems you guys are going to get to work are 10 times more difficult. Well, let's see, 4,000, 200 times, do math, 200 times more complicated than the stuff I thought I was doing a good job with, because we're looking at these reservoir sections, and I'm looking at trying to figure out how the pressures work. Woo! Crazy. Anyway, and I'm going to use that forecast based on those reservoir parameters. The production data can be matched with analytic models. That's what we're going to look at here mostly. Widely available in commercial software, RPI, or numerical simulation models. Once the unknown reservoir and well properties are determined in the history matching procedure, that's where we're going to spend most of our time with it, the calibrated model can be used to forecast. Duh. Well, that forecast is what the money's all about. Am I going to make any money in the future? Okay, one. So what I'm going to look for is a way to do this in a practical approach. In a prior life, I was, my official title was Chief Reservoir Engineer. I was Chief Engineer for what became Anadarko. Most of you know who Anadarko is. I was actually Chief Engineer for the company as we spun Anadarko off. And I chose to stay with the original parent company instead of going with Anadarko, which probably wasn't the smartest thing in the world, but that's what I did. Anyway, at that time, my staff, there were 6 engineers and 40 clerks was my staff. That staff had responsibility for about 5,200 wells. And we were required every year to do the reserves evaluations and all that stuff. And this is what we were trying to do, was to try to find a way to understand what that EUR was. 6 engineers, 5,200 wells. You do the math. It was brutal. Anyway, the first pass. This is just a classic production decline curve, log rate, time. The purplish colored lines on here are the pressures, casing and tubing pressure. That's the water production. That's the gas production. The 2 gas lines, the bumpy one is the observed. The smooth one is the calculated. So basically what I'm showing you is the, you say, look at this patch. You say, Crafton, that's a crappy patch. Well, notice. I got the 2 lines to match clear out here. All right? So that was the piece of data that I was really focusing on, was what the well was doing at the end. All right? The log of rate versus time and the pressures. Jan did a fantastic piece of work considering the constraints that he had to work with. But I challenge you, I defy you to find any place in our classic theory that says there is any physical meaning to plotting the log of rate versus time. Now, you say, well, what does it mean? No, gotta be. The bad news is I know of at least 60 papers in one Petro that deal with trying to assert that there is mathematical meaning to that graph. There actually isn't any. Jan made no representations that there was. His agenda was to squish the data down enough that he could interpret it. That's why he did this. This had no basis in classic theory. Well, that's a real problem, because if we're going to spend, well, that's why I went over here. This graph, and anybody in here a chemical engineer? Oh, good. No, that's not good. I'm going to get hit. I hate to tell you that at Colorado School of Mines, the Petroleum Engineering Department had the bottom 2 floors of the hall, and the chemies had the top 2 floors. And so when I made this comment to the classes, I typically got roundly booed. So if I get booed today, it's okay too. Anyway, I told them, the chemies have an over us. And of course that was a bad pun, because they were upstairs. Chemies, when they look at transient systems, look at them from the perspective of mass rates. Pounds of stuff or kilograms of stuff per day or per second or whatever. They don't do business in volumes. All of our math, go back and look at some of the very oldest reservoir engineering textbooks. All of our math in petroleum engineering is based on volumes. Oh, no, it is. You haven't had it yet. Back in the day, I taught the second semester senior required class, and the best final exam question. I mean, you clean the classroom out in a hurry. define B sub T. What is B sub T? Total formation volume factor. Remember that one? Crossed that bridge before? Final exam. What is B sub T? Well, we typically talk about it in terms of volumes. Volume of reservoir to stock tank volumes, right? Wrong. That is actually wrong. Because it left out a really important concept. Suppose I had, coming into the stock tank, oil came out of the separator, right? The oil came out of the separator. The separator was operating for discussion purposes when the fire went out. Oh, crud. So the separator is at 40 degrees F and 150, 200 pounds, right? Bang. The oil came out of there and it didn't have all the gas knocked out of it, right? So suddenly I'm confronted with the fact that the oil going into the stock tank is not at the same conditions as the oil that I'm going to sell, because when I look up at the hatch on the tank, some of you have done this, I dare say, from the looks I see in the room, you see little wiggly lines coming up out of the tank. Natural gas. Dang it. B sub T is defined as the ratio of the two volumes, but in fact, it is defined as the ratio of the densities. It makes the fundamental assumption. How do you spell assumption? Well, assume. A-S-S-U-M-E. A-S-S-U? Don't like that one. You got it. I just made the assumption that the volumes related to the same weight of stuff. That's wrong. I just cited for you an example where the pounds of stuff changed, but I forgot to take it into account. Okay? So, when I look at this graph, if I do classic well testing, I'm going to look at volumes of stuff, and that's wrong. Okay? Just like B sub T being a volume relationship is actually wrong. It's a relationship of the densities because we are making the assumption that the weight of stuff stayed the same. And if it didn't, if we can think of situations in which it did not stay the same, and I just came up with one, I got a problem. So what I'm going to plot here, we're going to dig into this a whole lot more. What I'm going to plot on the y-axis is the pressure change divided by the weight rate, Q rho. So I'm going to do my very best that I possibly can to account for all of the pounds per kilograms. I don't care what units you use. I want to try to take into account all of the weight of stuff that relates to that pressure drop. Let's think about that a second. Suppose I had a pressure drop, and because somebody was stealing oil out of the tank, I've got the wellhead flowing pressure, and I think I know what the reservoir pressure is. So I've got a pressure drop. That pressure drop represents the energy being consumed by the system, does it not? Is that right? Oh, okay. But somebody's stealing oil out of the tank, so my denominator is wrong. What would I expect that thing to look like? What's that relationship going to be? Well, if the weight rate is measured correctly, it's going to be a measure of the amount of energy consumed divided by that which consumes the energy. Right? Ew, this sounds like thermal. Well, it sort of is. Anyway, so what I'm looking at here, this thing actually is an efficiency. The amount of energy consumed divided by the amount of stuff consuming the energy. So if it's doing a really good job, it's going to be low, right? Because the denominator is big. It's going to be upside down. And then in this case, I'm going to plot it against log of time. I'm going to defend for you. We're going to dig into the math in a bit. That slope of that line is the quality of the system. How the energy consumption changes over time. The elevation of the line measures the overhead. We call it skin. We call it effective wellbore radius. We call it effective fracture length. We call it completion efficiency. All right? The slope is the transmissibility, is the reciprocal actually, of the transmissibility of the system, and the elevation is the overhead or skin. Oops, go the right way. There we go. Yeah, we're not done. So, I hate using this because I keep bumping the wheel. When I do these evaluations using that approach, I'm going to be able to use a reliable technology. And this is one of the pieces that John really focused on. How do I understand the reservoir behavior in these systems? Well, that's why we've got to defend the theory. We're going to use this reliable technology, and they defined it as being reliable as 90% of the time it got right answers. That's pretty. Well, here's this is a portion of this. There's actually 200 and some different examples that were pulled from our SPE literature that they used as the basis for making that assessment. And this was actually some of the results that John let me have back. These are examples pulled from different SPE papers, the supposedly given values and the match values. You don't need to dig into it, but that was basically the support behind why they said it was okay. RPI meets the SEC requirements. It's got several parts to it, obviously. Yeah, he showed me an equation. Yeah, we're going to have to dig into that a little bit because that's our guiding light, as it were. But look, high school algebra. Y equals mx. Huh? We're going to spend a whole 2 days talking about y equals mx. Yeah? I have the audacity, the arrogance, whatever you want to call it, to push on you. That horrible looking equation that I wrote up there in blue ink is nothing more than y equal, it doesn't even have a b. It's not even the equation b. B is equal to 0 in this case, the way that equation is written. So all of a sudden, I am confronted with the fact, you thought, well, this is really going to be hairy. You guys got an E1 function up there, got Greek letters. Yeah, that's just the language I'm using to try to describe to you the physics that theoretically is nothing more than the equation of a straight line. All right? We're not talking about college stuff. We're talking about sophomore high school stuff. What we're doing is we're using that sophomore high school stuff to try to understand something. No, that's not right. We're using that high school stuff to try to assess, get a sense of, have some feeling for the physics of the real world. Okay? Now, why is that important? Well, that's kind of a lead into this topic we're going to spend another 20 or 30 minutes on here just now. But the point I want you to wrestle with, to whatever extent you feel that this is just hairy stuff, just, oh my gosh, I don't think I'll ever understand it. Wait a minute. You just made a horrible admission. Because what you admitted to me was, assuming that was the admission you made, what you just admitted to me was, I am not prepared to understand the equation of a straight line. I dare say that had you gone to the admissions people here at Tech, if you'd gone to the admissions department and said, I don't understand the equation of a straight line, they would have invited you to go up the hill to Albuquerque to the university. Respect. I rest my case. You got the point. Therefore, and the reason I want you to come from this point of view, I do not want to let you have my objective. One of my objectives is I don't want to give you the opportunity to run hide because the stuff is too difficult. It's just the equation of a straight line, and that straight line goes through the origin because b is 0. All right? That's all we're talking about. That's all we're talking about. So with that idea in mind, the first thing we need to wrestle with in that context is how does that fit? Can I begin to understand that simplistic relationship in the context of a physical system? Well, my belief is adamantly, yes, we can do that. So, the next piece is this idea of confirmation and normalization. As I told you at the outset, there were these A, B, and C pieces. First of all, the fact that the only interpretable data was that data that had 0 rate. And I made the assertion to you that there is no such thing as a system that has 0 rate. They don't exist. That doesn't happen. Well, it happens before the drill bit goes through the reservoir. Wait a minute, question. Ooh, hold it. Let's see. The drill bit goes through the... Anybody ever been on a drilling rig? Great. What was on the drilling rig over in the doghouse that was referred to in a variety of different profane terms usually as the mud log or the gas chromatograph or that's... We took mud logs all the time, right? Very routine practice to take a mud log as we're drilling. The objective of which, holy Moses. Don't do that again. Almost as much fun as going to the dentist, wasn't it? Not. What happens when we take a mud log? Driller dudes, talk to me. What are we doing with the mud log? What happens? What is the mud log measuring? And? Yes, I agree. But that's not all.
Gas content?
Say again?
Gas content?
Yeah, the amount of, well, let's change that slightly. Because some of the original chromatographs only saw methane. But a lot of the chromatographs we're using now will go up even through C12 and plus.
Right.
So we're measuring hydrocarbons. Hydrocarbons that are released by the system. Yeah? We agree with that? That's what a mud log does. Wait a minute. If a mud log is measuring released hydrocarbon, say it carefully. The mud log is measuring hydrocarbons released by the system. And yet we want to carry mud weight enough that we do not have a blowout. Right? I mean, that's one of the reasons we put mud in the hole, not the least of which is to lubricate and carry cuttings and all the other stuff. But the fundamental issue is we want to carry enough mud weight that we've got pressure control. Yeah? I mean, that's what we looked at in drilling class. I know you did, because that's what we do. But wait a minute, if that's true, if that is absolutely true, then how did that stuff get into the wellbore? How did that hydrocarbon, be it liquid or gas, doesn't matter much, how did it get into the wellbore? The pressure of the mud weight is so high that we do not get a blowout, but when we looked at the mud log, we saw some hydrocarbons. That doesn't make sense. That doesn't make it. Fundamental law of physics, damn physics. Fundamental law of physics, stuff moves from high pressure to low pressure. Right? Categorically, always. Let me say that slightly differently. Stuff always moves from high energy to low energy. And that takes into the ideas cap pressure, takes into the ideas wettability, takes into the ideas of interfacial tension, takes into account all kinds of other stuff that can be part of the energy of the system. Right? See that? Does it make some sense? Now, wait a minute. I wound up on the mud log seeing liquid and gaseous phase hydrocarbons. Therefore, they must have come from some place that had higher energy than that represented by the mud. Whoa, that ain't good. Well, stop and think a second. It ain't bad, simply because when the stuff moved into the reservoir, dang it, sorry, guess I can't wave my arms. Boy, that'll be a short lecture. Crafton can't wave his arms. Well, we're done now. That was quick. Sorry. Got to do something. The problem, the conundrum is, how did that hydrocarbon phase get into the wellbore if the mud weight was higher than the pressure in the reservoir? Well, it didn't. The mud weight isn't the driving operative process. The function of the mud, that's why we put fluid loss material in there, remember? That's why we talk so much about mud cake. One of the objectives of the mud is to create a mud cake whose function it is to create enough skin or enough apparent damage that flow no longer occurs. And if the mud cake fails is when we have the blowout. If the mud cake doesn't build fast enough, if the mud cake does not remain competent, that's what constitutes a blowout. Look at Macondo. Oh, let's not look at Macondo. The point I want you to think about is for the instant that the drill bit is penetrating that little chunk of rock, the pressure in the reservoir is probably, categorically it is, otherwise I would not see a signature on the mud line. So, mud weight, why does that got to do with this? Well, it's got everything to do with this because we're back here thinking about what things affect this straight line equation. What I just confronted you with, reservoir pressure will always, well, will generally be higher than the weight of the mud column. The mud column is a predictor of the least possible reservoir pressure. Now, I said that, and I just committed an utter heresy.